We'll motor along with looking at centripetal motion, and before we even begin, and we're still continuing with circular motion, let's ask ourselves, where do we experience centripetal motion? In the two easiest examples I have, first, is when we drive a car around a corner. That is absolutely, that does say corner very roughly. Let me rewrite that when I'm looking at it. Does not look good. Around a corner. And where else might we experience a centripetal motion? Well, this one, if you ever go to a fair or you go to an amusement park, you see that one that spins in a circle. To me, it makes me sick. I cannot experience it that well. You feel the G-forces, and that is that gravitron ride spins really, really quickly in a circle. We also experience centripetal motion there. When we're talking about our circular motion, we should note a few things. First is that for any object that's undergoing uniform circular motion, and this is a common misconception, so that's why I would like to tell you guys this right now. So uniform circular motion. The speed of the object is constant. And what does that mean? That means that the speed stays exactly the same. However, the direction is constantly changing. So what does that tell us? Our speed is staying exactly the same, but the direction is constantly changing. This implies that the object is in fact accelerating. Why can we say that? Our speed is constant because our direction is constantly changing. That means your velocity is changing because the direction is changing. Since our velocity is changing, that means our object is accelerating. Second thing that we should note before we analyze centripetal motion mathematically is the fact that the magnitude of our centripetal acceleration, and that's what we're going to be looking at today, or in this video, is constant, but the direction is always changing. Therefore, the average acceleration is directed towards the center. That's all that means about our centripetal acceleration. It is center seeking. So let us now analyze centripetal motion mathematically. So here's what we're going to do. Make sure I'm at the top of my page. Let's analyze this mathematically. Let's have a coordinate system set up here as follows. We have a y and an x axis. And let us look at uniform circular motion, and I'm hoping that my freehand circle is as close to a true circle as possible. It's not the greatest. Please forgive me for that. We're going to choose, say, 2 points on this circle. We're going to choose right here, let's say, for example, and this will be represented by A prime. And at A prime, we might have a velocity at that point of v1. And this is very similar to the tangent of a line. Right at that point, we have a line that we can draw to represent v1. This is the velocity right at point A, the instantaneous velocity. And we might also have, let's call another point A, let's just call it A. And right at that point, tangent to the curve, we could have our second velocity, v2. So let's analyze this guy briefly. Our origin at O. Well, the only way that we can analyze this, we have our radius of our circle, and although this circle is not drawn as a true form, please do keep in mind, because it's supposed to be uniform circular motion, these two radiuses are supposed to be the same. And we will call this length from A prime to A as our arc length in a straight line. Let's call that S in this case. We notice that our change in velocity will be equal to v2 minus v1. That is our definition of our change in velocity. But to add this using vectors, we must say that our change in velocity will be v2 plus negative v1. And this is what makes it really nice in this case. If we have v2, draw a very similar representation. There's my v2. Negative v1, so it's acting in the opposite direction as a vector. Tip to tail, we have joined our vectors. That means our change in velocity can now be calculated there. And that's my resulting vector here. And let us call this triangle A, B, C. All right. These two triangles are similar because we're using both V2 and V1. So we could say, since triangle AOA prime is similar to triangle ABC, that tells us that the ratios of their side lengths are the same. Well, this is going to help us get or derive a few formulas that are important for centripetal acceleration. So that tells me that if I take delta V and put it over any one of my V1 or V2, that will be equal to the arc S, the length of the arc, over either one of my radii from the uniform circular motion, S over R. However, there's one case that comes up. What happens if T is very small? Well, if T is very small, our arc length between A and A prime approaches a straight line. And this straight line represents the distance traveled. So that tells us S will be equal to the distance traveled, which is delta t. And we all know from the very first unit and from grade 11 university, our displacement or our distance is simply equal to v multiplied by our time. That means that this value here can replace s. So therefore, what we have going on now is delta v over v is equal to v delta t, which represents the arc length s, all over r. We're looking to analyze acceleration. Remember that acceleration is equal to v over t. And I should say that the change in v over t. Let's try to manipulate this formula so that occurs. If I multiply both sides of my equation that I have here by delta t and multiply by v, which is on the bottom here, I would have delta v over delta t, which is part of my acceleration, would be equal to, well, if I multiply by v, that gets us v squared over r. But again, remember, acceleration is v over t. Therefore, my centripetal acceleration, AC, can be defined as the speed or the velocity over r, and that's velocity squared. This is one of our main equations that we can use to calculate the centripetal acceleration of an object in uniform circular motion, in which velocity is always changing. We're traveling around a circular path. And because we're traveling around a circular path, we can say that for a circular path, the distance traveled is the circumference of a circle. And remember, the circumference is 2 pi r. And this is completed in one period. Remember, period is represented using t. And one period is the time it takes to complete one spin. So speed, which is distance over time, the distance is the circumference, 2 pi r, over the time it takes to complete one cycle, the period t. Well, what does that do with centripetal acceleration, which is v squared over r? Well, let's substitute v in. So that would give us 2 pi r over t squared, and all of that's over r. Manipulating this formula, we get that our centripetal acceleration is 4 pi squared r over t squared. Dividing fractions out, that's how we get a new equation for the centripetal acceleration. Oh, but let's continue even more. Remember that the period can be calculated because it's an inverse relationship of the frequency. So therefore, my centripetal acceleration can also be calculated if I substitute 1 over f in for t. Now it will now give me 4 pi squared r f squared. So we have 3 different calculations that we can actually use to calculate the acceleration that you might experience if you're in, for example, the gravitron or taking a curve along a road. So let's say, for example, that you are a race car driver and you enter a circular curve with a radius of 30 meters at that constant speed of 25 meters per second. What's the car's centripetal acceleration? Well, what are we given in this case? We're given radius. We're given a constant speed of 25 meters per second. SI units, speed in meters per second, beautiful. Radius in meters, beautiful. We can easily calculate what our centripetal acceleration would be. So AC is V squared over R. We can calculate that. We'll take 25 squared and put it over 30 to see what we would get. 625 divided by 30, 20.833. How many significant digits? One significant digit. So 20 meters per second squared is the acceleration that that car is undergoing. And there we have our centripetal acceleration for the car. Let's continue with one more brief example, and this is dealing with the moon, which orbits the Earth with a period of approximately 27.3 days. And the distance from the Earth to the moon is approximately 3.8 times 10 to the 5 kilometers. So there's approximately our radius. We must change days into seconds first. I'm going to show us this using conversion factors. It's how my brain works. So I know that I have 24 hours in one day. That means days cancel out. I'm now in hours. I need to now convert this into minutes. So minutes, I know that there's 60 minutes in 1 hour. Hours cancel out because they're on the top and the bottom. My units are now in minutes. Let's convert that into seconds. So that will be 60 seconds for 1 minute. I see minutes cancel out. We are now in seconds. Let's calculate how many seconds in 27.3 days. You'll hear me punching my calculator. Yes, because I have not done this question yet. Which is 2,358,720 seconds is our period. Our radius now, 3.80 times 10 to the 5 kilometers. Let's convert that into meters. There are 1,000 meters in a kilometer. So that will be 3.8 times 10 to the 8 meters. We have our radius, we have our period. Let us calculate our centripetal acceleration. That will be 4 pi squared r all over t squared. And that will give us 4 multiplied by 3.14 squared, radius of 3.8 times 10 to the 8. And that will all be over 2,358,720 squared. Let us see what our centripetal acceleration would be. And assuming I punch this into my calculator right, if you want to check just to make sure, I get 0.002128 meters per second squared. Let us check our significant digits. 3 significant digits. So 0.00213 meters per second squared is the acceleration of the moon.